defining monads in a modular fashion. So the traditional approach, which was proposed in '95, is monad transformers, and that's been widely accepted in the Haskell community. But more recently, there's a new contender, these algebraic effect handlers. And last year, we've seen several papers that have shown us how to implement them in Haskell. So why are these effect handlers interesting? Well, as previous work has shown, there's a very nice methodology for developing new effects and implementing them with effect handlers, which is much more complicated with monad transformers. And also the composition of multiple effects is almost for free, or pretty much for free with effect handlers, whereas there can be many complications with monad transformers. So that's all very nice, but in this work we're looking at another property that we're interested in. So when we're combining multiple effects, we also want to look at how are these effects going to interact with one another. So let's investigate that property. And here you have an example of a program that uses two effects, the decrement program. It uses both state and exceptions. And here this is an implementation with monad transformers, where we first get the current state, we check whether it's strictly positive, and if so, then we decrement and put back the new value, and otherwise we throw an exception. How do we run this program with monad transformers? Well, we choose an order for the transformers, and we run the transformers in that order. So in this example here, we're first running the exceptions and then the state. And then we get the result. In this case, we get a tuple of left unit and 0. And the left unit indicates here that an exception has occurred and the program has been aborted. And the 0 tells us that at the point where the exception happens, we had the state of 0. All right, but this is one choice. What we can also choose is to run our transformers in a different order. We can first run the state and then the exceptions. And in this case, we get a different kind of result. We just get left unit. We don't get any more information about the state. Okay? So we have a choice here in which way we have an interaction between the two effects by running the transformers in a different order. So that's very flexible. That makes it easy to control the interaction between the two effects. And that's a very nice property of monad transformers. So we want to make sure that this property is also preserved with effect handlers. And yes, we can write the same program again, now with effect handlers. And the only thing that has to change in the program is the type, actually. And running the program happens in a similar fashion as with monad transformers. We again have these run functions, but now they are called handlers. And they're going to assign semantics to the different operations. And we can choose in which order we run the handlers for the two effects. And then we get, in this order, first the exceptions and then the state. We get the same behavior as with the transformers. And if we change the order of the handlers, we get another interaction. So we get the same behavior, exactly the same behavior as with monad transformers. So again, a very flexible way of controlling the interaction between the two effects. So that's all good. It looks like both approaches are equally good on this account. But should we really generalize from just one example? Now let's have a look at another one. Here's the triple decrement program, which is going to decrement 3 times in a row. And there's a new operation here, which is the catch operation, that is kind of creating a local scope for the last 2 decrements. And when an exception happens in this local scope, in one of the 2 last decrements, then the catch will intercept this exception and we'll pass it on to the handler, which in this case is just a trivial return, which is going to turn an abortion again in a successful completion of the program. Now, if you're looking at the interaction between exceptions and state here, there are actually 2 possible interactions for this program. One which I call the global update semantics, which works as follows. Suppose we start with a state value of 2. After the first decrement, we get 1. And then we enter the local scope of the catch, where the decrement will turn the state into 0. And the last decrement, because the state is 0, will throw an exception. This will be intercepted by the catch and passed off to the return, which will finish the program. But what happens with the state is, well, we just take the state from the local scope and pass it on back into the global scope, and that's the final state we get, is 0. Now, the local update semantics is slightly different here. So at the point where the exception happens in the local scope, we don't pass on the state that was as it was modified in the local scope. We will go back to the last state before entering this local scope, and the value 1, and this is the value that we pass off to the return, and that's the final value of the program. So 2 possible interactions here, and of course we want to see those possibilities again when we're running our program with Mona transformers. And that's easy, just choose one order for the, running the transformers. And in the first case here, what you get is the global update semantics, and running the transformers in the other order gives you the local update semantics. So that's cool, we get this flexibility of choosing which interaction we want. Great. Okay, so Mona transformers are holding up. And with effect handlers, okay, we can write the same program, we can run the handlers in one order. And what we get here in this order is the global update semantics, nice. But if we run the handlers in the other order, what we get is again the global update semantics. So it seems that changing the order of the handlers does not affect the interaction semantics. There's no way here that we can get this local update semantics by changing the order of the handlers. And it's a real disappointment. We get the fixed semantic interaction, and it turns out that in this case our algebraic effect handlers are not as good. And it's a real pity. They're not as flexible as Mona transformers, so maybe we should forget about them altogether. I don't think that's a good idea, so let's just set out and fix the problem and make this example work as well. And to make algebraic effect handlers as flexible on this account as Mona transformers. So in order to fix this problem, we have to understand a little bit about what's going on. And the first question is, well, why was the second example different from the first one? The second example had this operation catch, and something was different with catch. Well, the general idea with effect handlers, if you have operations, how you're going to implement them. Well, if you have simple atomic operations, like get, put, and throw, these are implemented in 2 parts. We split them up in the syntactic part and the semantic part. The syntactic part is going to be captured in a functor, that's just representing the syntax of the operation, and the semantic part is going to be captured in a function that's going to interpret the syntax and assign some semantics to it. Well, this is different with scoping operations that have a part of the program in a local scope, like catch, because in these operations, well, we might want to do the same thing. We might want to separate the syntax and the semantics in the handler function, and the syntax is going to define the local scope for part of the program. Well, this doesn't work because these operations like catch, they don't fit the required functor shape that is demanded for all operations. And that means we cannot express them as syntax. And that's a pity, but there's a workaround that's already been used a lot, which is to say, well, if we can't have the syntax part, let's do everything in the handler function. Let's have it both handle semantics and also define the scope for us. And that's the solution we're actually working with here. And that makes operations like catch different from operations like get and put. So when we were looking at this problem and trying to get our local update semantics, we were trying to change the order of the exception and state handlers, but that's really been a red herring, because the semantics for catch is not really in the exception handler. The actual semantic interaction is going on between catch itself and the run state handler. So we should be looking at changing the order of these two to get a different kind of interaction. All right, so let's do that. Let's take the catch and put it after the run state, and then we will get indeed the local update semantics. So wonderful, problem solved, except there's a little catch, I should say, and that's that if we move the catch from its position up there and put it after run state, then we at the same time modify the scope that the catch sets up. And now the scope is no longer over this small subprogram, it's going to scope over the whole program. And of course, that's also going to affect the behavior of our program, so we don't want that. So what we have here is a catch-22. We can get the interaction semantics we want, but then we may destroy the scope that we want, or we may get the scope we want, but not the interaction semantics we want. So that puts us in a bind. And how to solve the problem? Well, it's very obvious how to solve the problem. We should again split up the 2 aspects of scope and semantics, and that's what we're going to do in this paper. We're going to capture the scope again in syntax and only the semantics in the handler, so that we can control these 2 separately, so get the interaction semantics we want without affecting the scope that we want to have. So the solution that we're using is to propose a new shape for the syntax. The previous shape was kind of first order shape, and what we propose is a higher order syntax shape. So here's the current approach, the first order syntax approach. If you want to capture the syntax of an operation, you have to look at how you want to write this operation in the program, and you have to take into account that there's going to be a continuation to this operation. So here for throw has one parameter, the exception you want to throw, and then after throw there's going to come some kind of continuation at the remainder of the program. To capture this in syntax, we will set up a new data type for this exception operation. So we have a constructor throw, and we also have two fields. One is for the exception, and the other field is for the continuation. The type of the exception, we'd like this to be polymorphic, so we choose a type variable x, and that's going to be the type of the field, the first field of the constructor, and we'll parameterize our data type over this x. And then the continuation has this type. It's going to take the result from the throw operation and continue. In this case, we can expect anything to come out of a throw, so we'll have a type variable a here, and then we have the result type of the whole computation, which is going to be this free monad, that's called proc here, over some kind of signature that represents all the operations you may have in your program, and then the result of the monadic computation has some type b. All right, so we want to take this type and use it also for the field of the throw constructor, but we're not going to copy the type exactly. We're going to change it a little bit, and what we're doing here is we're taking this result type and we're abstracting it. So we're forgetting entirely what structure it has, and we're just turning it into some abstract return type R, just a type variable that doesn't tell us anything about the shape of this result type. And we're going to parameterize our exception type over this R. And now you can see that this exception operation has a functor shape. It's functorial in this R. This is a hole where the continuation goes. All right, so let's do the same thing for catch. Let's try to put it in this shape. Our catch has two parameters, P and H. The P is the program in the local scope, H is the handler, and then there's also a continuation K that happens after the catch. All right, so we have another constructor in our data type for exception operations, the catch constructor with three fields for P, H, and K. And so K is similar to with the throw operation. It takes the results from the catch and then continues in this free monad. So we get the same type for the continuation in the constructor. We play this abstraction game, abstracting the result type to just a single type variable R. And then P and H, here are their types. So they're also not simple values, they're also computations in this free monad. They don't return a value of type B, but they return an intermediate value of type A that's going to be passed on to the continuation. And okay, we would like to put these types in the other two fields. And well, we have a problem here. You might think we could write just the type R again, but R is also capturing the B. And here we have not a B, but an A. And that's a problem, so we can't use R here. We don't have a proper way of abstracting these and expressing them in terms of R. And so what we get is this type here, which is not a valid form for the approach. We haven't really been able to abstract all of the computational types in this representation. So this is a bogus representation that won't work in the approach. And we need to fix this somehow to make catch behave properly. And actually the solution is not that difficult. So what we've done before is we've taken this whole structured result type and abstracted it to a single type variable R. Well, the solution is to not abstract so much, just abstract a little bit less. And remember that the result type has a monadic structure. So there's a monad M. We're going to forget what the particular monad is, but we remember that there is a monad, and then we have separately the result type B. And that's interesting because now we can mention separately at the abstract level the monad M and the result type B. And we can use the M in positions where we don't have to combine it with the B. And that's what we'll do for catch. So the result type at the bottom of the continuation here is MB. This is the abstraction of the result type. Now we can use the M in these positions combined with the intermediate result type A. So we can properly abstract here, and that's the representation that makes this work. That's the representation in which you can express catch as syntax. And so we've taken this representation, which is actually a higher order functor now, and we've adapted the whole approach, the whole framework using the free monad. We've adapted that to this higher order functor shape. And then there's a small requirement on the handlers that have to be expressed now in a compositional style. But then you can implement everything in this form, in this more general form. And yes, you can express the triple decrement program then. And now this program is entirely made up of syntax. There are no handlers in this program. Catch here is going to be expressed as syntax. And all of the semantics is in the handlers. So we can choose our order for the handlers, and we get the global update syntax in one order, and we get the local update syntax in another order. So this is the right approach, where we have recovered the flexibility of choosing the interaction between the state and the exception effect. So this is the way to go. And so let me wrap up. What we've seen here is that handlers should not be used to determine the scope. We should leave that to syntax. And the way to go is to use higher order syntax for this, rather than the first order representation. There are more details in the paper that I won't go into. There's an introduction to effect handlers explaining how the whole framework works. We have more examples in the paper that show situations where this problem arises, where you want to have flexibility for the interaction between effects, like for example in parsing with cut or in multi-threading. And besides the higher order solution, we first show a partial solution using the first order syntax, using begin and end markers to set up a scope. But this does not cover all the situations where you would like to use scoping constructs. And of course, you can find all the code in the paper. So in ongoing work, we're looking at how to use more efficient representations for the approach, optimizing the free monad, and there's a talk tomorrow on how to do that. We also want to understand how we can use this higher order syntax approach in strict languages. Last year, Kamar has shown how you can do that with the limited control, and it's not clear yet how that carries over to our higher order syntax. Another interesting aspect is we've required that handlers are compositional, and this has revealed to us that actually handlers are usually false, can be expressed as false, so we'd like to be able to exploit that property. And of course, we don't want to lose all the existing infrastructure for first order syntax, so we're also working on lifting that infrastructure to our higher order syntax level. Okay, that's the end of my talk. Thank you very much.
We have time for a few questions.
So thank you, Tom. That was beautifully done. You talked about the interaction between effects, but to me, one of the most important parts of the effects is the equations you expect them to satisfy. So you briefly mentioned get and put. That they aren't just syntax; they come with a bunch of laws about how they internally relate to each other. And when you then start combining those with other a separate class of effects, you might want to think about the operational properties, the equational theory of the whole. How does that fit into the story?
So we haven't really worked out exactly how this works in general, but you can see there's when you run handlers in different orders, there's some kind of distribution going on, and this tells you, you can derive from this what kind of equations you will get between the operations of the different effects.
So it emerges from what you've done, or it still requires extra thought?
It requires some extra thought to make it explicit and general, but I think you can derive it from the approach. Yeah.
Okay.
Thank you for a nice talk. In your types, you had to have a monad in your handler type, right? Because you had an MA.
Yeah.
Yeah. So one of the nice things with handlers is that you don't have to have a monad as a return type. You can just have to give any type there, right? Which is kind of what the problem was. So now you have to, if I do want to do that, I have to factor everything to another monad and then reinterpret that. So I kind of have to layer another first order handler over your higher order handler. I'm asking you. So
if you always have to wrap it in a monad, but if the monad has no interesting structure, then you can just use the identity monad, if you like.
No, but not every type has a monadic structure. So one of the things you can do with first order handlers is that you just need to choose any type and give it an algebra structure, not necessarily a free algebra structure for the model you're trying to handle.
But we're looking here in particular at the modular situation where you have a free monad with lots of different effects in them, and you write your handlers in this modular style where you're going to just handle a single effect, and then you're going to leave the rest of the monadic structure of the other operations there. So these handlers, there's always going to be this monadic structure there.
Maybe we should take this offline.
Okay.
Thanks.
I think it's almost exactly the same question, but thought about in a different way. I would say that you try to make into an algebraic effect handler something that is not algebraic, that you found a nice way to inject back monads in this same interface. Does that seem like a fair characterization?
So yes, we're assuming that we have like a monad that is made up of different effects, so operations belonging to different effects, and you want to handle a single operation and not handle the rest of the operations, because you want to isolate the treatment of different effects in separate handlers. So these handlers have to be aware that there are going to be other operations there that have a monadic structure, but they don't have to know what those operations are. They're just going to care about the single effects that they are implementing.
Thank you for this nice talk. It looks like this type here. Is it a monad transformer?
It's an F and then algebra.
It is. It is in a sense. It's not a monad transformer because it doesn't give you a return. So the return is missing here. It's a functor transformer. So it's a higher order functor. It takes a functor and gives you back a new functor.
Okay. Thank you.
Okay. Let's thank Tom again.